In this video, we will discuss the function q of x, which is usually used in while performing the bit error rate analysis of digital modulation schemes. So you will encounter this function whenever you are trying to evaluate the performance, the bit error rate performance of different digital modulation schemes. Well, this function is also called the complementary cumulative distribution function. It's also known as the complementary cumulative distribution function. We will most likely observe the relationship of q of x with the standard normal PDF, which is denoted by p of x, the standard normal PDF, or the CDF, the cumulative distribution function, which we will denote by phi of x. So we will see that this function q of x is actually related to the phi of x, the CDF cumulative distribution function of standard normal distribution, or the PDF. This is the PDF of a standard normal distribution. So before going to the expression of the function q of x, let me rewrite the cumulative distribution, the expression for the PDF, for the standard normal PDF. If you observe the general expression, for the Gaussian probability density function, the Gaussian, if you observe the general expression of the Gaussian probability density function, it looks like this. P of x is 1 over under the root 2 pi sigma square e raised to the power minus x minus mu whole square over 2 sigma square. So this is the generalized expression for the Gaussian PDF with mean value mu and the variance sigma square. So keep in mind these parameters. The mean appears here, the variance appear here in this expression p of x, and if you want to draw it, you can draw it on the x-axis. If you draw it as a function of x, right, you can just draw it. It would be a bell-shaped curve with the mean value mu and the variance. Usually the variance controls this spread, right? The variance or the standard deviation controls this spread. So it means if the variance is high, you will have more spread. If the variance is low, you will have less spread. So the p of x can be observed as a function of a single variable x, right? So it means that the values of mu and sigma square, which appears at the right hand side of this equation, they will have some fixed value. So if now this Gaussian PDF is called the standard normal PDF when we take the mean equal to 0 and the variance equal to 1. So if the variance is 1 and mean is 0, the PDF, this PDF is called the standard normal PDF. So let me plot it here first. If your p of x, if your mean is 0 and sigma square is 1, if your mean is 0 and sigma square is 1, your p of x The expression for the p of x, just substitute these values, would be equal to 1 over 2 pi e raised to the power minus x square over 2, right? So we substitute this mean 0 and variance sigma square in the above expression, and we get the new expression for the p of x, which looks like this one. Now you can observe it. It's very easy to plot this expression in octave. You just take the value of x, as you are those who are familiar with the octave code. You just take this these values in this range from -5 up to 5 with a step size of suppose 0.1. So if you take this x and you write expression for your p of x, right? P of x in the octave, just write this expression, which is very simple. Write this expression and you just use the plot command. Use the plot command to plot x and p of x, and x and your p of x, which is denoted by this one, right? Because we have to use this variable. So when you plot this command, and you just write you have to write this expression, right? Here you need to write the expression. You need to write this expression for this right hand side. So just write the expression in octave and just plot it. If you plot this one, you would get a bell-shaped curve. You would get a bell-shaped curve like this, and the on the x-axis, right? It's because we are taking the x values here, and its mean would be 0, and the spread, you can see that it would be from -5 up to 5. So you will get this bell-shaped curve. This is the theoretical curve for p of x, right? This is p of x, a standard normal PDF. Now there is another function which is related to the now when we say this is standard normal, we have the expression for the standard normal, and we can see that our PDF looks like this one, with the mean value 0, and the spread, or the spread is actually the spread is 1, the variance is 1, so the sigma square, the standard deviation, is 1. Now another function which is very closely related to this p of x is known as the cumulative distribution function, or we denote it by phi of x, and this function is actually the integral of p of x, the integral of this, or let me change this variable, the integral of p of t dt from -infinity to x. So this value, p of t or p of x, if I just change the variable t over here, p of t on this t axis, the shape doesn't change, right? Everything remains the same, just change of variable, t is equal to x. Just for the to be accurate, I write this p of t in this expression. So if you see this integral, what is actually this integral? This integral is actually the value. It gives you it gives you this area from -infinity to some point x. It gives you the right, or I should say the left, the probability of the left tail, right? This phi of x. So it's actually this area. This is the probability, or you can say the probability, that the random variable x, this random variable x, would take some value in this range from -infinity up to x. So this is the this is defined by the CDF. This is defined by the CDF. So now another we come to the function q of x, which is very closely related to phi of x, or you can say p of the PDF or the CDF. So if we see the function q of x, the function q of x, that is defined as 1 minus phi of x, right? 1 minus phi of x. Now if you say 1 minus phi of x, now keep in mind, if you integrate the PDF, if you integrate the PDF from minus infinity to plus infinity, just recall your previous knowledge. If you integrate the PDF, any PDF, if you have a PDF and you integrate it from minus infinity to plus infinity, you would get unity, right? This curve is, the whole integral is equal to 1. So if you subtract, this is actually the this one is the area of the under the PDF, the whole curve. So if you subtract the area which is given by phi of x or the CDF, you would be left with the area which is towards the right. So which means that if you have a bell-shaped curve and you subtract this area from 1, so you will be left with this area which is towards the right of this point x, which is towards the right of this point x. So phi of x, phi of this is some point x here, or let's say x naught to be specific, if you are not to be confused with the x's. So if you have certain point x naught, and you that phi of x naught would give you this area, right? Phi of x naught. And when you subtract this from 1, you would be left with this area towards the right, which is q of x naught. In other words, if you want to write expression for q of x, if you want to write expression, mathematical expression for q of x, now you can write it easily, that your q of x is actually equal to x to plus infinity p of t dt. This is your q of x, right? So it gives you the area towards the right side of the point x. So it gives you this area, it's towards the right side of this point x. So q of x is in other words, we can say that q of x is actually, let me write it specifically, that q of x is, we can say 1 minus phi of x related to the the CDF, right? Q of x is related to the CDF, or you can write it using the PDF of the standard normal curve. Now keep in mind, this P of t is a standard normal curve, not the generalized Gaussian PDF. So we have to take for q of x, we define q of x. This is phi of x CDF is defined for generalized Gaussian probability density function. You can define cumulative distribution function, but when we talk about q of x, then we should have a standard normal PDF. P of this should be a standard normal PDF. So it means that specifically, to be accurate, specifically my q of x would be actually equal to the integral of from x to plus infinity, the integral of this p of t, which is standard normal PDF. And if I say my p of t standard normal means 1 over the expression is 1 over 2 pi e raised to the power minus t square over 2. So if you substitute it over here, your q of x is actually equal to 1 over under the root 2 pi integral of x to infinity e raised to the power minus t square over 2 dt. So this is your q of x. This is known as the complementary cumulative distribution function because of that property that it gives you the instead of the left tail probability, it gives you the right tail probability, right? So q of x more specifically, if we have this variable t, our q of x gives us the right tail probability of a standard normal curve. So if so this would be given by q of x. This area, this whole area would be given by q of x. It's the right tail probability. And this is very important. If you see the different digital modulation schemes, your error probability appears as in the form of q of x, which is the complementary cumulative distribution function. So it appears in the form of q of x. Now keep in mind, if your x is greater, your q of x would be smaller, right? Later on we will see that the value of x we would see that while having the bit error rate performance, we would see that this x actually corresponds to corresponds to SNR. The x actually corresponds to SNR. So when your x is higher, means your SNR is greater, your q of x usually refers to the bit error rate. So your bit error rate is less. When your x is higher, your bit error rate is lower. And of course, when signal to noise ratio, higher SNR means a strong signal at the receiver. Higher SNR means a strong signal at the receiver. So when you get a strong signal at the receiver, you would expect the lower error rate. You expect that your bit error rate is lower. Now let's try to see one more point. Let's try to observe one more important point about this q of x. Let me draw this bell-shaped curve once again, and your q of x is actually the right tail probability, right? So if I put a line here and x point is selected over here, this point is an x point. So q of x is the right tail probability. It is the right tail probability of standard normal PDF, right? So your q of x is the right tail probability of standard normal PDF. Now because the PDF is standard normal, so the mean is 0, it's symmetric about the origin. The PDF is symmetric about the origin, so it means that the probability that the random variable would take these values, which is given by this area, right, which is given by q of x. You can think about minus x. And minus x from minus infinity up to minus x. This because the once again I would repeat that the curve is symmetric about the origin. So this area is equal to this area. Right? This is graphically, I'm just showing it to you that the area from x to infinity, area under the standard normal curve from x to infinity is equal to the area of this standard normal curve from minus infinity to minus x, right? So if you have an expression, now keep this in mind, it's a very important point. Usually you will encounter in the bit error rate performance that if you have an expression which is given in this form, that your PDF is integrated from minus infinity to minus x. So this is same this is equal to the integral of the same standard normal PDF from x to plus infinity. So we say that this is equal to q of x. The same is true for this one. This integral is also equal to q of x, right? So we can write that q, this is the same as q of x, right? This is the same as q of x. So whether you get an expression, these limits are very important. Keep this in mind, because these limits are very important. If you integrate it from x to plus infinity, you would get the right tail probability of the standard normal curve, which is the same as integrating the same curve from minus infinity to minus x. Now here it is negative of x, from minus infinity to minus x. So whether you get your mathematical expression for the better performance in this form or in this form, you can represent it as q of x, right? It is actually q of x. So this usually you will encounter both of these expressions. Sometimes you may get your result as your integral in this form, sometimes you may get it in this form, and keep in mind it is the same as q of x. Now let me draw this q of x, because you draw the PDF, right? You can draw the PDF, you can draw the CDF for the standard normal curve, and let's see how this q of x looks like. If you draw the q of x on x-axis, right? If you draw it, you will see that it appears something like this. And this range is actually from -5 up to 5 for the standard normal curve. If you observe it, somewhere here is your origin 0, and the value here is 0.5. The maximum value of this function, this is q of x, this function q of x, the maximum value of this function is +1, and the minimum value, like it is 0. Now theoretically speaking, it should be +1 for x equal to minus infinity. The reason is that expression, as I told you earlier, that q of x is 1 minus phi of x, right? And this is the CDF. When we say this is the CDF f of minus infinity is 0. So you get q of x equal to 1. For standard normal curve, we get from -5 approaches to 1. So at -5 it is this approaches to 0, phi of x approaches to 0 for standard normal curve, and we have the q of x approaches to 1. Now as the value of x increases, now you can see, let me plot another curve as well, the PDF, and I would like to explain it with the help of this this curve. So let me plot the PDF curve. Now when you have a minus infinity somewhere here, right, minus infinity, or if we talk about the standard normal curve, as I said, that the standard normal curve is actually it extends from -5 up to 5, it is 0, right? So for -5, knowing this area is 0, which is given by phi of x, minus infinity up to x, right, from -5. So this is 0. You are getting 1. This whole area is 1. Area of the whole integral 1 minus something 0 is 1. So you will get this point. So if you increase this x, if you move here towards this point, your x is actually increasing in this direction. So if you increase the point x, your function decreases monotonically. And it approaches at 0. You have half of the area is already. So this CDF, this function has value 0.5, so you get 0.5 here at 0. Now from onward, 0 onward, if you increase x, it further reduces from 0.5 and approaches 0. So actually on a linear scale, if you plot your q of x, it looks like this. It's a monotonically decreasing curve. It's a monotonically decreasing curve. You can also plot it on the log scale, and the log scale, if you take the vertical axis, if you take this vertical axis on, as a logarithmic scale, so if you take the vertical axis, if you have x-axis, and the vertical axis for q of x is taken the same values, right? You do not change the values, but you just change the scale. This if this vertical axis, this one is on the log scale, if it is log scale, if it is plotted on log scale, you would see that the curve appears like this, somewhere 5 minus 5. So it's actually from 1 up to here up to 5. So it's the vertical scale now plotted as a log value. The log values of the vertical on the vertical scale, we have the log values, or we say the log scale. If you plot it on the logarithmic scale, you would see that q of x is actually a monotonically decreasing curve. It's a monotonically decreasing curve. So you can, and if you observe the bit error rate performance of digital modulation schemes, you can see it. You can see, or later on you will see it, that actually those appear as a decreasing curve, monotonically decreasing curve, because they are in the form of q of x. So I hope that the function q of x would be clear now. And we covered almost essential knowledge of this complementary cumulative distribution function, and we came to know its relationship with the PDF, standard normal PDF, and with the CDF, the cumulative distribution function.